Hi there, this is Toby, and welcome to a status update on the Time Machine. I thought I'd start with a little bit of Brazilian music this time. Put ourselves in a good mood. I'm gonna fade this out. Okay, I'm gonna fade this out so that this video doesn't get taken down, hopefully. But anyway, I thought I would do a sort of a status report on the research project I have been working on and off for a while now. The main repository for this project is the Playlang repository, which stands for the Play programming language. But as the project description says, the Play is a programming language intended for use as a testbed for various compiler, runtime, and debugger technologies. And the particular thing I'm working on right now is the Time Machine, the time traveling debugger, which I have explained in various videos. So if you feel like you would like to get more detail about that, please watch those previous videos. This is going to be a status update, as in I feel kind of lonely and just working on this by myself without anyone to talk to, bounce ideas off of. So this creating a video like this, if nothing else, lets me talk about it. And best case scenario is one of you watching can actually give me some feedback and perhaps give me some ideas about it. Okay, so what have I been working on? So I actually published a lot of live coding videos of myself working on this Deep Zoom debugger in the past. And then later, I have this repository, a separate repository for the Deep Zoom debugger. There it is. But I've created a couple of introductory videos explaining the Deep Zoom debugger. And actually, I might just play one of those for you to just give a very, very brief overview, introduction of what that is. And my computer is a little bit slow because I'm trying to record this. This is only a 5-minute video. I'm not going to play all of it. Actually, it might actually be better to, instead of playing. So it's largely inspired by Google Earth, the concept of Deep Zoom. And if you go here, you'll see that with this debugger, you can kind of zoom into the execution of the code, like so. So this is a Fibonacci function. You can keep drilling down into the recursion. And then I also made a video with my colleague Koichi Jo explaining the concept to her, and she gave me some pretty good feedback about it. What I've been working on more recently, in the recent maybe 3 or 4 weeks, is sort of merging the code in the Deep Zoom debugger back into the Play programming language, and I will sort of show you that. So at this point, I have this Tic Tac Toe game, which I will show you, but before that, let me just show you like a very, very simple program, say something that counts to 10. So this is a program that counts to 10. And we're able to, let's see if this works. I have a web compile command which will actually compile a program like this for the web page to execute. Let's see if this works. So you end up with this. This is actually currently optimized for a canvas-based application, which this count to 10 application isn't. But what you do get is this debug button here, which if you click on it, will allow you to let me move this in so you can see all of the controls. So you can step backwards and forwards in time, and you can see the variables state at any point in time. Again, this is similar to the Python tutor. This is a step debugger where you can walk forward and backwards in time. There's also this zoom button you may have noticed, which if you click, it switches the step debugger into the zoom debugger. And with the zoom debugger, you can actually zoom in and see this visualization of what the program is doing. And the way a while loop is visualized in the zoom debugger, it's actually, it just repeats the while loop over and over again. Every line that gets executed is served display on a separate line, and whenever there's an assignment to a variable, it shows you the value that was assigned to it, so you can follow the execution of this code this way. We don't have anything that helps you visualize what it prints out, unfortunately. I imagine if we had that, it might be like a little transcript that's on the side, but you can also traverse it, the value of the transcript over time by hovering over here, maybe. I'm not sure. Okay, so that's what the zoom debugger looks like when it's integrated into the language. Oh, I want to show you the Tic Tac Toe game now. One idea that I got from watching Jonathan Blow's videos. Jonathan Blow, if you don't know him, he created a programming language called JAI for the purpose of making high-end games, of which he's in the industry of doing. And what he has that really works well for him is that while he's building the programming language, he's actually using it to build a real production level game on the programming language. So he gets sort of real feedback from real world usage scenarios. So I took a page from that and tried to build something that's closer to a real world scenario. I haven't fully gotten there yet, but I'm approaching it that direction. Building out basically more complex applications that can be considered more real world. And I was thinking of building a chess game actually, but I thought that's kind of hard. Let's build something slightly simpler, and that is for me that was a Tic Tac Toe game. So let me show you that Tic Tac Toe game. Okay, so this is the Tic Tac Toe game. I can play against the computer. I wrote an AI for this Tic Tac Toe game based on the Minimax algorithm, which is already giving the debugger some troubles, which I will explain later. So I'm going to play a couple of games here. And if I go into debug mode, again, I'm able to use the step debugger to step backwards in time, and I can also use the zoom debugger. Let's step backwards, and we'll step into one of the games that was played. There's a draw board function that draws the board. If you want to step into the draw board routine and step through how the board was drawn, you can do that. By the way, this is a HTML5 canvas that is drawing on top of. I provided functions for the runtime in the runtime for the program to draw to, and have these arrow functions for stepping out, stepping in, etc. Human move, that's human move, and if you're wondering how the computer AI works, well, here's this smart computer. You can step into the code line by line and so forth. Let's look at it using the zoom debugger though. So this is the zoom debugger, and you could see that using the zoom debugger very quickly, we played 2 games. and I can zoom into the execution of the first game. I actually have done a lot of work on the visualization of the arrays and dictionaries. So currently the board looks like this, which I think is a pretty good bird's eye view of what's going on. So I can see, oh, first human move was the O in the center, and then the first computer move was over here, etc. And if you want to drill down more into how the computer works, you can drill into this smart computer function call, and then most of the meat of what happens is in this smart computer calculate move function, which I hope it will let me drill into. But one problem I have yet to solve is when the text gets too small versus the aspect ratio of the box. Sometimes the layout is slightly wonky. But anyway, so there's the code in the next level. So this is a recursive function call. So for each function call to smart computer calculate move, it calls it again for each possible move at that level. And what it does is basically tries every move. So like it finds the first open square and then tries that. It's like, imagine that I moved here with this imagine move function, and if you give a board to the imagine move function and say I want to move myself to that square identified by that index, it'll basically generate a new board for you, which would be the result of you having made that move. And then given that, it calls itself again to calculate the opponent's move on behalf of the opponent, see what the opponent would have made. This is based on, again, based on the minimax algorithm. Okay, so all of that to say that once I did this, I actually saw huge performance problems, and in particular, if it's like, first of all, it's already very intensive to run this AI algorithm on a very small board. This is just a Tic Tac Toe game with 9 squares. I don't even know what's gonna happen with a chessboard, right? What happened was when the depth was significantly high, up to level 5, then the entire browser just froze. And I found that the memory usage was way up. It was up to like 200 megabytes, more than 200 megabytes of memory usage for that browser tab. And then the browser just froze. I guess the Chrome didn't want to give this tab any more memory. So I thought long and hard about this problem, about how I could fix it. One way I could fix it, obviously, is to improve this implementation of this AI algorithm to make it use less memory. But that's actually not the point. I'm building a programming language runtime, and I want it to be able to handle big loads. So even though the minimax algorithm is obviously implemented in a very poor way, I don't want the fix to be the algorithm itself, but I want it so that the time machine can do what it's supposed to do, but even when it's having to deal with a large load. So the reason that it was using memory way too heavily is because at this moment, at the code that you're seeing right now, the program actually saves every single state of the program itself in memory. That's what allows you to step backwards in time, because every single state that the program has been in is saved into memory. And what happens when we exceed the available memory? Well, the program just dies. So instead of doing that, what I decided to do was, okay, we're no longer going to store every single state of the program in memory. We're gonna let the previous states be reclaimed, and we're just gonna not keep references to them anymore and allow the garbage collector to take them and reuse them for the current program. And instead of that, we're gonna save that state into a database. We're gonna save it on disk, so that it's no longer a memory problem, but it's a disk space problem. Let's defer the problem onto the disk. So that's what I did. I decided to use SQLite. I considered using, actually, I went down this path of, like learning how to build a database myself, and there's very little information about how to actually build a database, but I did find a few, and I was actually going to do that, but stopping short barely. I decided to design a database schema and just build this using SQLite and possibly LevelDB as well. As I think that both of these are good choices for what I'm doing, because both of them are in-process databases, and you save the data into a single file instead of requiring like a database server. Okay, so I implemented that. JSON-R is a JSON-ish format that I made, which I'll explain a little bit later. So let me now switch to my database branch. And I'll just stash. Okay, I want to show you a little bit of how that works now. So I did a bunch of database work, loading the runtime state of the program into a SQLite database as the program is running. And so to give you an idea of how that stuff works, if I compile a program now, let's say this Tic Tac Toe program, and that generates this JavaScript file. Okay, there's actually a lot I'm gonna have to explain. The current state of the thing is the code. I decided to bring the runtime back into Node.js instead of being in the browser. So now the Node.js, the Tic Tac Toe, I made a terminal version of the Tic Tac Toe program instead of the canvas version. I just ported that one to be a terminal-based version. And now, when this is the generated code when you compile the Tic Tac Toe terminal version. Okay, so this is the Tic Tac Toe terminal version. Instead of using, like if you look at the draw board function, for example, instead of using fill rect to draw the board, it's just gonna use the print command to print it into the terminal and so forth. But the computer code actually mostly did not change. The AI code that uses the minimax algorithm, it stayed the same. So I still get to test that part of the code, which was the point, is like when the execution of the program blows up in complexity, can I handle it? And what happens is I have this function to initialize the SQLite database at the beginning, which gets called here. And it creates the tables that are needed, and it will initialize the file basically. And then I'll generate these prepared statements for inserting into the database. And I have two functions. One is called the send objects function, and then another one is called the send there's three functions: the send function call function, the send snapshot function, and the send objects function. Each of them will take the state, a particular snapshot of the state of the program, and insert it into the database using one of these prepared statements. Okay, and because all of the objects in the programming runtime are immutable, when you mutate things, it just generates new versions of the objects instead of mutating actual objects. There's no worrying about mutating the records in the database. Everything that happens to the database is an insert. So that made that part of the implementation quite simple. So we're just inserting a whole bunch of objects into the database. So let me try to run this Tic Tac Toe game here and show you. I hope it still works. Okay, so you can pick a move between 1 and 9. I'll pick 5, which is the center. And it's running the AI algorithm now, which is actually taking a while. It took 5.7 seconds. I believe it's probably a little slower while I'm recording this video, because my video recording software actually takes a lot of CPU. But when I tested last, it actually took about 2 seconds for the first move, which has to do the deepest traversal. So I'm going to block this X down here with 7, and I win the game. So now I'm going to say no, and once I stop the program, a history file is generated, and that history file is actually a SQLite 3 database file, and I can open it up. So let's open it up to see what's going on. Where is it? Oh, there it is. Okay, so the first thing you see is that there's a fun call table. Every record in the fun call table is a function call, is a particular function call with particular parameters. And you can see the parameters column is actually a number. That number is a reference to an object in the object table, right? And I'll show you that. So what it says is there's 2,919 function calls made in the execution of that game, and we see the function name of each of these function calls. There's also the snapshot table. A snapshot is a snapshot of the state of the entire program at any one point in the execution of that program. So there are 80,000, more than 80,000 snapshots of the program. Each snapshot has an ID. It has the current stack state and the current heap state, and each of those again is a number. It's an ID to the objects table. Interrupt is a thing that I also invented a little bit earlier to store when I was implementing the canvas implementing the canvas drawing and trying to figure out how to walk backwards in time and still have the debugger update the state of the canvas back to what it was. I use something called the interrupt, which is whenever you send a message to the canvas, I capture it in here so that later on I can play that back. That the debugger can play that back. So, but that's not used in here because it's a terminal app now. And then we have a line number corresponding to that snapshot saved into the database. Now let's look at the object table. Object table has an ID which is referenced by the other two tables, and then it's got this data which is in this JSON-R format. And JSON-R is another project that I created as an npm package, which you can install this way. It's basically JSON with refs. It allows you to define these IDs for your objects and arrays, and you define it like this. So this says I define this object as ID 1 and so forth. And later on you can refer back to 1 by using *1. *1 is a reference, and this and sign is a declaration of this ID. So that's what JSON-R is, and the objects stored in this object table are in JSON-R format, so it can have references to other objects in this table. And you can see we made a lot of objects. And I'm actually hoping I can find a way to reduce the data usage, but at current moment we actually have 152k, close to 153k objects created as a result of running this little Tic Tac Toe game, which seems excessive, and I'm sure there's ways to optimize it. But that's what it is. I have not updated the Zoom debugger to be able to read from this database and provide the visual experience that it does. That's one of the next steps in my project. One thing I want to mention is that as I was working with SQLite and was doing some performance tuning, on npm there's a couple of packages for working with SQLite. There's just the thing called SQLite. There's SQLite 3, and there's better SQLite 3. SQLite is just a very small wrapper around the SQLite 3 package, and SQLite 3 is the most current version of SQLite, by the way. But the author of SQLite, he actually started an effort to create SQLite 4, trying to implement the structured log merge tree concept, which is in Google's big table, but he abandoned that project, and so SQLite 4 is no more, and now the current version of SQLite is still SQLite 3, and that's what these Node.js packages are going to be talking to. However, when I did some performance testing with these packages, I wrote some scripts to load test inserting a very, very large file into SQLite sequentially using, this one uses better SQLite 3, but I had another one that was using just SQLite. Where was it? This one that's just using SQLite, and I had some performance problem related to my own libraries, in particular the JSON-R library being slow. After solving some of those, I did run into that the SQLite package itself being slow, and after switching to the better SQLite 3 library, the performance did get a lot better. So in terms of performance, the better SQLite 3 npm package is definitely better. I did also consider, instead of using one of these npm packages, to go down to the C level and write the code in C, which I might still explore in the future to get even better performance. But to give you an idea of the performance, I took a profile of one of these Tic Tac Toe games that I played, and this is the flame graph for the execution that, by the way, if you generate a program, if you compile a program in the play language, it also, right now, I should make this an option, but currently it always does it. It uses the Node.js inspector, the Chrome inspector, to take a CPU profile of the program as it's running. So that's another reason it might be slower. But what happens when this happens is you can actually load that profile into Chrome like this. You just click on this button. Let's just do that. I'm gonna find that profile file that I just created by playing that game, and load it in here. And now you can kind of ignore those warnings. And now this is the profile flame graph that was taken by the Chrome inspector as a result of running that game. And now I can look in detail into what the code is doing and what part of the execution is taken most of the time. And currently it's two things. The yellow dots and the blue dots, or the parts that are not yellow dots. The yellow dots are actually the writing of the data to the database. That's the this exec function is actually the SQLite driver, the better SQLite 3 driver doing its job. But other than that, I got this $stringify function, and that's my code. And that's what I can optimize. And I'll show you my code. So this function is my code to stringify, take an object and stringify it into this JSON-R format. And I already rewrote this function once to improve the performance, but even after that performance optimization, it's still one of the biggest bottlenecks currently. And you can compare the performance of this stringify, which is taking like 57% of the total runtime, and then this run is taking 27.7%. And then I also have register new objects and imagine move. The imagine move is the actual code of the program itself, right? So if I can improve the performance of this stringify substantially, that will also help with the performance. And just to give you an idea of in terms of what the performance I'm targeting, obviously I would like the performance to be negligible, but currently if I run that same Tic Tac Toe game without this logging going on versus with logging is about 33 times slower, I believe. I can run that comparison again. So I just ran it, right? And I got like about 5.7 seconds of making that first move. If I turned it off completely, all I have to do is put a early return in this function and this function, I believe, and then it will not do any database logging. Now let me play that Tic Tac Toe game again. This doesn't seem right. Oh, I changed this in the wrong place. I changed it in the file that was going to get overwritten. I should change it in the runtime file instead. And again, things are much slower with me running the video recording software at the same time. So the data may not be very accurate here, but I'm still gonna do it just to show you. So this only took 429 milliseconds to make for the computer to make the first move, and that means it's actually about only 13 times slower with the saving the state versus not saving the state, and that's pretty bad. Although, you know, given the benefit that it gives you, I think it's probably still worth it. But I basically want to improve the performance as much as possible so that it's viable for use, right? So that's what I'm working on. The next steps of what I'm targeting is, first of all, update the deep zoom debugger and also the step debugger to be able to read from this database, use the data from the database to drive the UI instead of using the in-memory objects to drive the UI. And then number two is I want to further optimize the stringify function so that the overhead of logging the state is as negligible as it can possibly be. One thing I might do is try to implement that code in C instead of in JavaScript, and hopefully that helps. Yeah, so that's where I'm heading. Thanks for watching. If you have been watching this far, thank you very much. Feel free to give me feedback about this project, as I would love to hear from you.